Hello, everyone. Now I want to introduce Heverson. You can
Yes.
introduce yourself a little bit, and then
Yeah.
I will go down.
Hello, my name is Heverson. I'm from Web3 Foundation, research engineer at Web3. And today we are going to actually have two presenters. I have my colleague somewhere there that is going to show up, Syed. And today we are going to talk a little bit about BEEFY, right? So let me check if everything's go well. So if you ever thought about turning your light client from loaded Himalayan Sherpa into a Usain Bolt-like client, we hope that this talk is going to give you a glimpse of the path. Is it okay? The path to achieving that, right? So we are actually starting by just giving some definition about light clients. We are going to talk a little bit about consensus on Polkadot and try to understand why you need BEEFY. And after that, we are going to give an overview of the protocol and try to show the both way of implementing that. So in the distributed systems, the first question is what is a light client, right? So in distributed system, usually a fundamental problem that any designer or developer faces is how to ensure that in an environment that you have multiple nodes, how can they agree on the final state of the system? So in this system, usually you have a subset of nodes that they have to, in the case of Polkadot, they are the validators, right? A subset of full nodes that they are required, for participating in a process, in a consensus process, in order to determine and agree in the final state of the process. So the issue here is that this process, the consensus process, requires a significant amount of resources. So and it limits the type of devices that you can use, that you need to use to participate in the consensus process. So a light client is a piece of software or protocol that allows the resources, the devices that are constrained in terms of resources, to participate and to follow the consensus process. And then they can identify in which state the participating nodes agree upon, right? So both full nodes and light clients, actually, they want to follow the consensus and to know what is the actual state of the system. But what are the main differences between them? So a full node is fully connected to the peer-to-peer network. A light client, in the other hand, it's connected, usually often connect to a single full node. A full node listens to all consensus messages that are passing in the network. A light client is completely out of consensus, so it doesn't listen to that. A full node also has a replica of the full state. While the light client is not really interested in having this, it's only interested in very specific block headers that can be used to validate some specific transactions, right? So in any case, that light client need to rely in a full node in order to access the state. And we have this issue that we're going to discuss a little bit more, that a full node may be malicious. We cannot trust in it. So what are light clients? Why they are useful then? So let's see in this very simple example, in this use case, when somebody is trying to just buy a coffee in a coffee shop and pays with his or her mobile wallet. So the transaction is created between the clients, right? Then it's signed, sent to the network in order to expect it to be included in the chain. So later, if this client wants to check if this transaction was added to the final state, it needs to act with a full node and ask this full node the state. Then the issue here is that it gets it, but we know that a full node can be malicious. So how can the client, the light client, believe in this information that the full node sent to him? So in order to understand if he can believe or not, we need first to understand how the consensus work on Polkadot, right? So Polkadot, actually Polkadot relies on Grandpa, with the protocol Grandpa, in order to agree in the final state of the chain. So Grandpa, that stands for greedy, heaviest, observed, sub-tree, recursive ancestor deriving prefix agreement, which is something, right? So what that really means. So in Polkadot, actually, every nodes actually vote in rounds, right? So at every round, at each round, full nodes that are part of the validator set, they are going to vote for subtrees. So these subtrees are subtrees that they believe to be the best fork for the canonical chain, right? So nodes are voting in these subtrees. And by doing this, we know that nodes are going to have different points of view concerning this. So node 1 here, for instance, he thinks that E1 is the best block for the network, for the chain. Node 2, E2, and node 3, D3, right? So every single node has a different point of view from network. But Grandpa, in the end, is going to make this consensus rule that it's going to I don't know what's happening. The Grandpa validators actually will agree that in the common ancestor, right? So for every common ancestor that 2/3 plus 1 of the nodes voted for, so they are going to Grandpa is going to define that this is the finalized block of the network. So in this example here, anyone can tell me which is the finalized block? No? So this example here, this is the last finalized block. Here in this example, I'm considering 2/3. Officially, it's 2/3 plus 1. But in this example here, for instance, 2/3, you have 2/3 of the nodes that voted for this. So the intersection of the ancestors, the common ancestors are there. So this is going to be the last finalized block. So you might think now, okay, why the light client just don't follow the Grandpa votes and say, okay, this is our last block. Why we just don't follow this? So, and actually there's a reason for that, because Grandpa justifications requires the full data of each validator. So as I said, validators are voting for subchains. So for each subchains, you have a number of ancestors. So you have to include the headers of these ancestors in the finality proof. So, and every single round, you have about 1,000 validators voting for that. So the amount of data that you need for that, it's kind of important. So another point is that Grandpa justification uses ED2 5519 signatures, which is not aggregatable, and it's not easy to verify in EVM if you are, for instance, putting your light client in a bridge, right? So what do you need? We need actually an efficient way to verify our finality proofs, right? And Grandpa doesn't give us that. So what is the solution for that? So the solution is BEEFY. So we are actually adding an extra protocol over the consensus, the Grandpa consensus. And this, what it brings us, more efficiency proofs for block ancestry, because we are relying on MMRs, Merkle mounting ranges. If somebody doesn't know what it is, we can discuss about it offline. It's a Merkle tree, right? It's a specific type of Merkle tree. So we also with BEEFY, we are also adding a new round of votes that there, instead of voting a subtree, now every single BEEFY validator is voting a single thing. And this single thing we are going to show that afterwards, but it's the main difference now we are not voting for sub-trees and their ancestry anymore. We're going to vote for a single thing. And BEEFY also brings a kind of friendlier crypto scheme based on ECDSA or BLS that can be used, that is compatible with EVM, right? So basically, BEEFY consists of two components. One extra voting round and a light client-side protocol. What is the consensus extension or our extra voting round? This is the example that I want to show. Different than Grandpa, which is voting for different things. Here we are voting for a very specific and finalized Grandpa block, right? In practice, what actually the BEEFY validators are doing, they are actually voting for the MMR root of the blocks. The MMR root that validates or proves the blocks that were already finalized up to this point, right? So what is the second component, the light client-side protocol? The light client protocol, how can I say that? The main idea of this part of this component is that you have a prover, which is a full node, as I've seen in the other example. And this prover wants to convince some verifier, which is the light client, that a vote has been done and validators agreed in this block, right? So there are actually two different ways of implementing this. The first one, it is what you call the random sampling approach, which makes the prover and verifier to engage in an interactive protocol. And then there's the second approach, which is using SNARK. I'm going to talk a little bit about this first approach, and then my colleague Syed is going to keep with the SNARK part. So what's happening here? What happens here? So you have the prover that sends a claim to the verifier. What is this claim? This claim has actually, it doesn't have the signatures or all the keys of the validators in this case. In this case, actually, the most important thing that you have here is a bit vector that shows which are the validators that signed that vote, that they voted for that. So what the verifier does, actually, is going to select some random nodes, some random validators that voted for that, and is going to ask the prover to send their keys, right? So if the prover can send the keys and the openings that can prove that all those validators that he was implying that they had voted for that, so then the verifier can either accept or refuse this proof. So this is the basic idea. I'm not showing code more than that. This is just a commitment. And you can see that you have this bit vector there. So the second approach, which is the SNARK, I'm going to pass the word to Syed to keep the explanation. And for those that are expecting equations, be prepared.
I'm here. Okay,
yeah,
now I have a microphone. Cool. How does this work? Okay, cool. So that was one approach, the random sampling, and you saw there's a complication, and you have to go back and forth and get and getting randomness. If you are writing a light client on a bridge, is not a trivial thing, because usually blockchains are deterministic. So basically, you have to wait for a bit, so you get randomness. Then you can ask those questions, and because of that, we came with this new approach, which is using a protocol called Web3 Sum, which has been developed by Web3 Foundation researcher. and is a generic protocol which basically allow somebody to verify a statement that is signed by a subset of signatory committee, which here is the validator, but anything, without knowing individual public keys of those committee. So you only need to know who has signed, and you need to get the signature and an aggregated public key, which I talk about, but you don't need single public keys, which was basically the biggest problem in the random sampling part. So using that, you don't need public keys. You can skip the random sampling part of your write client, or your write client become much more simple. So how does it work? So from so high-level overview, overview is that it uses BLS signature. So that is not very surprising because BLS signatures are aggregatable. So instead of having many signatures, and then again in the random sampling algorithm, you had to go and say, okay, give me this signature that you said you have, and then verify it. You aggregate all of them, and you get one signature. So this has been known. So and Ethereum used BLS because of that. So the signature can be aggregated and become only one signature. So that is one thing. And this one signature can be actually verified with a one aggregatable public key. So if you have the aggregated public key and aggregate signature, then you can easily verify them. The only problem is now why this is not actually like, you know, out there used is basically the aggregate public key has no indication that it was done correctly. Is actually I did the full node actually added all those public keys and got one public key. They could just take something random public key and say, okay, I claim that is aggregatable aggregated public key. So I'm just putting this together. So what we got from BLS was that we were able to add all these 1,000 validator signature and get one signature. The bad part was that the public key wasn't the aggregation process of the public key wasn't transparent, and so somebody might come and say, okay, maybe I have 1,000 validator every session. Maybe I just send this 1,000 to the light client, and then they can aggregate as much as they want themselves. But at least every message that I send only one signature. So this is one gain. But the problem is that light clients are not online all the time, for example. Yes. So if you come and give me the 1,000 public key of this session, how can I believe these are actually public key validators? So you have to validate them for me. For that, you have to show me the signature on the previous set validator signed over these public keys. And then how are you going to believe the previous one, and so on? So you have to go back to Genesis, everybody sign on this, and every time you have 1,000 public keys. So this becomes a lot of things. So to resolve this problem, basically, we designed this protocol. So you don't need all the public keys. You have a prover node. The prover node will aggregate the stuff for you and give you the aggregate public key, but also it'll come with a proof, with a SNARK proof, that basically they did the aggregation correctly and they didn't cheat it in that. As a result, you have this aggregated signature and aggregated public key, and also now you have this short SNARK proof that basically says you didn't cheat it in this process. And the light client will accept if the SNARK proof passes, and if the public key basically passes the verification of the signature. And then basically you are done. You got the state. You don't need to go back and forth, random sampling and stuff. So what do you need if you're writing a light client? You need this verified commitment to the public key. So still you have this problem that you cannot trust the public keys of the validators. But if they are signed with the previous session, then you can get it. But this time you don't need all these public keys. You only need a commitment, which is 2 points on elliptic curves. So now still you need to go, if you're starting your light client just right now, and you have no indication, no saved data to say that these validators are valid, you have to go to Genesis. But for every session of Polkadot, you only need 2 points of elliptic curves. So if there has been like 3,000 sessions since the inception of Polkadot, which is not, it's 2020, I guess, till now is like a 600 session. Every day one, oh, every era when you validate your change. So every day one, for every day you need two elliptic curve points. And then you have this commitment, and using that now you can believe in the commitment to the public key of current validator. You get a bit vector that says, this is part of BEEFY already, that says who has signed and who has not signed this specific BEEFY commitment. And this is 1 bit per validator, so it's 1,000 bit, which is much, much smaller than having 1,000 public keys. And then you have one BLS signature, which is aggregate of all signature, and one public key, which is aggregate public key. And now from the relayer, you get this proof of that this public key has been aggregated correctly. So if you look at the code, this is the verifier code. It's very, very short. There is no back and forth. Basically, you see you got the aggregated public key, you got the proof, and the signature and the message. At the first step, it will go to this KZG verifier. Basically, you verify the commitment. Using the commitment to the public key, you verify that the aggregation has been done correctly here. So you start the verifier, you tell them what was your public key, set of public key commitment, the 2-point, and then you give them the proof. And the verifier will verify that the aggregated public key was correct. And then after that, you just you make a public key, you run a simple signature verification, and after that, the light client will completely we'll know about the state of the chain. Here, I just wanted to just give you some overview that how this happens. Like if you're writing light client, you don't need to if you believe us that the protocol is right. But I just want to tell you like how this magic happened. And instead of having 1,000 public keys, now we ended up with just 1 point and elliptic curve. And this happened using a SNARK. SNARKs, basically what will happen is that if you can interpret your problem in a set of polynomials, then using a SNARK and polynomial commitment, basically you can convince a verifier that the aggregation, the verifier that those polynomials, you know them and you know, and they are correct, without sending them the polynomial. So you end up with a huge polynomials, but instead of sending the polynomial to the verifier, you can convince them that you have these polynomials that satisfy some property that the verifier wants to satisfy, but without giving them the polynomial, only giving a commitment and opening to those polynomial. Like 1 point of the like you can give them few points on polynomial, and then they will become convinced that that you have those polynomial. And so here, basically, what we did, we had to translate this polynomial into this problem into some set of polynomials. So these are the main set of polynomial, like auxiliary polynomial that we made, and this is like the bit field polynomial. So at this is each validator point. It is 1 if the validator has signed, and is 0 if the validator hasn't signed. PKX is the x coordinate of all public keys. PKY is the y coordinate of all public keys. And this is these are the accumulator polynomial. So these are the aggregator polynomial. If the public key, if the validator had participated in the public key, you added, this is additional elliptic curve. You add it here. And these are following the x coordinate and y coordinate of the aggregation. So basically everything is a polynomial, and then we are lucky because additional elliptic curves are also polynomial. So these are basically the identity we are basically verifying. These are huge polynomials, if you see, because this polynomial every point should basically represent that if you added the x coordinate or didn't add the x coordinate, this is the beginning of the accumulation, this is the end of the accumulation. This is the simplest one. If you want to look, I just show you that it's not very scary. It basically says the bit field polynomial that you're telling me that you have is only have value 0 or value 1 on the validator points. So you see this polynomial can be 0 only if bx is 0 or 1. So basically this is the way we verify this polynomial, but then I don't send you this polynomial, I send a commitment to them. That is how this become much smaller, and basically you get a much more agile BEEFY. So the random sampling BEEFY is already implemented on Kusama. This one has not completely been implemented. I don't know what happened. OK, it comes back. So part of it, so the crypto part of it is under the way. The verifier and the prover has been implemented here, and the messaging part between the relayer and light client has not been implemented yet. But that is a very short part, basically just sending these messages when somebody asks for them. So that is the state, and I hope in a few months we'll have this functional on a testnet. Thank you very much.
Thank you very much. We still have time for one question. Is there a hand? I come. Shortly the name and then the question.
Hello, my name is Dan. I was curious, is there any verification done before? So there's a proof of how the aggregated public key is created from all these public keys, but how is there any verification done that these validators are the actual assigned or like selected validators?
Yeah, so here, the first part, oh, what happened? Now you don't see me. OK, it came, good. This one, yes? So I assume that you have a constant commitment to validator set, that you believe in it. So this basically is that polynomial that I showed you for all the validator set. If you believe in this commitment, then you believe in the validator set. Now, you need to believe in this. So this is in the BEEFY message from the beginning. So you get a BEEFY message from last session that this is inside it, and because you believed in the validator previous set, this was there, you verified the aggregated signature on that set, and this was just a message. So it's just part of the message, you believe in it, now you believe in it, you can now use it for the next session, all the messages. And then the next session is one of these, so during that session you will verify the next session validator key. So you still have to go to the day one of Polkadot, as I said, but it's 2 elliptic curve point. There's 600 sessions right now on Polkadot, for example, era. So it's basically 1,200 point. If your light client just started now and he didn't know anything about the network, it's still doable. Thank you very much.
Thank you very much. If you have more questions, just hit him up. He's walking around. And now we will switch to laptops.
Thank you. Thank you.
Thank you very much.